direct form 2, cascade, and parallel form. So we discussed the direct form 1 and direct form 2, and I illustrated by use of examples how this can be done. So in this lesson, I will start it by doing another example, just to remind you of the implementation of a digital filter using direct form 1 and direct form 2. So let's have a simple filter in the form of y of n equal to 2y into n minus 1 plus 3y into n minus 2 plus x of n plus 2x of n minus 1 plus 3x of n minus 2. So let's consider the direct form 1. So we saw that for you to implement a filter using the direct form 1 structure, you need to bring an intermediate variable to represent the inputs. So that if the intermediate variable we have used is Wn, then we can say let Wn to be equal to x of n plus 2x of n minus 1 plus 3x of n minus 2. Then now we can be able to write our y of n as 2 into y n minus 1 plus 3 into yn 3 into yn minus 2 3 into yn minus 2 plus w of n. Once we have done this, then we can implement the direct form 1 in 2 steps. The first step is to consider the input x of n and a corresponding output w of n. So I will have my drawing in this form. I will have the x of n as the input, w of n as the output, and you can see w of n will be made up of delayed versions of the x. So I will use out the delay elements. We'll have a delay element there, x, z minus 1, another delay element, z minus 2, sorry, z minus 1. When these are combined, then because at this point, actually, at this particular point, we have a delay of z minus 2 because we have the first delay there, then we have the second delay at this point. So we are able now to tap our 2x n minus 1 here, because here we have x n minus 1, but we need to multiply it by 2. So what I need to do is simply to write the multiplying factor here. Then at this point, we tap in the xn minus 2, or the x delayed by 2 units. Then we need to sum those ones up by using a summer. You can see the direction of this. Then once you have done this, then we sum it together with the x of n, which is straight from the input here. So I need to have another summer here so that I can have my x of n here. Then I have this, so that here I have w of n. So that implements the first part of this. Then the second part, the input is y of n. So I will have the input y of n here. Then you can see we need the delayed version of y of n, delayed by 1 unit, delayed by 2 units. So I can have my first delay element at this point, second delay element at this point, so that we have z minus 1, z minus 1. So I'm able to tap in the yn minus 1 from this point, to tap in the yl minus 2 for this point. The multiplying factor for yl minus 1 is 2. Here I have 3. The same we would have included the multiplying factor here. So this, once I will add them up, then we add it to the y. You know, we add it to the w of n. Already we have this, we have added them, so we need w of n. So w of n, we get it from this point. So that now this one comes here, this one comes here, and then we have this. So we are able to get the w of n. So this would be my direct form 1 implementation. Direct form 1 implementation. Then we looked at the direct form 2 implementation, where we saw that you still need an intermediate variable, but now we can look at it as working in the Z domain. So this means that we'll start by obtaining the Z transform of the given function if it was given in the time domain. So we'll proceed through the same example, but now have our implementation in the direct form 2. The function still remains the same. I'll write it down here for ease of reference. So we'll have y of n equal to 2 y n minus 1 plus 3 y n minus 2 plus x of n plus 2x of n minus 1 plus 3 x of n minus 2. So I will start by obtaining the z transform of this function. And if we do that, we will obtain y of z equal to 2 z negative 1 y of z plus 3 z negative 2 y of z plus x of z plus 2 z minus 1 x of z plus 3 z minus 2 x of z. Basically, we want to obtain the transfer function. So it will mean that I will write the like terms together. I will collect the like terms together so that I have y of z minus 2z minus 1 yz minus 3z minus 2 yz equal to xz plus 2z plus 1 xz plus 3z plus 2 xz. So that means the transfer function hz would be given by yz over xz, which would actually be 1 plus 2z plus 1 plus 3z minus 2 over 1 minus 2z minus 1 minus 3z minus 2. So at this point, once we already have the transfer function, then we can now bring our intermediate variable wz, so that I can write the expression as yz wz equal multiplied by wz xz should give us the same expression, 1 plus 2z plus 1 plus 3z minus 2 over 1 minus 2z plus 1 minus 3z minus 2. The steps from here are relatively simple because one of these terms I will equate to the numerator. And then the remaining one, I will equate to what remains, the denominator. So that we have yz over wz equal to 1 plus 2z plus 1 plus 3z minus 2. And the other term, wz over xz will equate to 1 over 1 minus 2z minus 1 plus 3z minus 2. I can call this combined function maybe equation 1 for ease of reference. So now we'll work with equation 1. Okay, I can call this maybe I can call this 1A, and then I call this 1B. Once we have done that, then I can, let me use 1A first. From 1A, we can clearly see that y of z would be equal to w of z into 1 plus 2z minus 1 plus 3z minus 2. Or simply we have y of z equal to wz plus 2z minus 1 wz plus 3z minus 2 wz. Then I need to come back to the time domain so that I have y of n equal to w of n plus 2 w of n minus 1 plus 3 w of n minus 2. I'll call this one equation 2. For 2a, call it 2a. Then from 2b, we also have, you can look at 2b. I can cross multiply 2b so that I have w of z, w of z minus 2 w of z for z minus 1 minus 3 wz z minus 2 equal to xz. Or we have in the time domain, I will have w of n equal to 2 w of n minus 1 plus 3 w of n minus 3, 3 w of n minus 2, sorry, not minus 3, minus 2 plus x of n. I probably call this a 2b. So we sort of come very close to the direct form 1 at this stage because the implementation would remain the same. I will implement the part where the x is the input, then wn still appears as the intermediate variable. So you can see that if I do that, then we start by implementing equation 2a, then I will have input x of n, then I need the delayed vessels of wn. So I need one delayed by 1 unit, another delayed by 2 units. So I have this delayed by 1 unit, delayed by another unit, z negative 1, z negative 1, so that I'm able to tap this having a coefficient of 2, having a coefficient of 3, have the summation at this point. Once I've had the summation at this point, then you can see we need to add our x of n. So probably we need another adder here so that I can have by, at this point now, I have the x of n. I have the x of n being added to the sum of this, which is basically this one term from here and this other term from here. So that is the first part. In the second part of the drawing, I will have to draw the 2A, where you can see we need delayed versions of WN, delayed WL, delayed version of WL, WN delayed by 1 unit, WN delayed by 2 units. But we already have the WL here. So you can see already we have WN at this point. So WN is already here that we want to get the Y of N. But the other, we also need WN minus 1 is here, except delayed by 2 units. Wn raised to power 2 is also here by 3 units. Then we add them there. So you can see, as we discussed here, you only need 2 delay elements because the delay elements are being shared. If you compare with this other case where you need, you actually need, here you need 4 delay elements. 4 delay elements. So we have looked at this, and this is called the direct form tool implementation. So the reason why we have relooked at this is because the other method that we talked about, the cascade method and the parent method, we still use the direct form tool. So if you understand how the direct form tool works, then it becomes very much direct to be able to come up with a cascade structure with very little effort. So we now proceed and discuss the cascade method of the filter implementation. Or simply cascade structures, or simply cascade structures. As the name suggests, when we connect block diagrams, for example, in cascade, then they are in series, which is opposite to the case where they are in parallel. And that's what we see here, that the method is simply a cascade of 2 structures. And those 2 structures are implemented in direct form 2. So let's look at this through an example. We will proceed with this by obtaining the Z transform of this filter and proceed and get the transfer function as well. So we'll have YZ equal to 3 over 4 Z minus 1 YZ minus 1 over 8 Z minus 2 YZ plus XZ plus 1 over 3 Z minus 1 XZ. Then collecting the like terms together, collecting the like terms together, you obtain the following. Actually, if you collect the like terms together and factorize, we can simplify this process to confirm this. Then I will have y of z, yz into 1 minus 3 over 4 z plus 1 plus 1 over 8 z minus 2 equal to xz into 1 plus 1 over 3 z minus 1 or we simply have y of z, x of z, which is equal to hz equal to 1 plus 1 over 3 z minus 1 over 1 minus 3 over 4 z minus 1 plus 1 over 8 z plus 2. So how do we go ahead and split this so that we have two functions that we can implement in cascade? So what we need to do if we have a fraction like this, factorize the denominator. This is really not getting the partial fraction form because what we want to do is very close to what we had in the direct form to implementation, where if we multiply two functions, we get the other one. So what we'll do, we'll start by factorizing the denominator that we have here. If we factorize the denominator, let's bring it and write it down here. So that I have 1 minus 3 over 4 z plus 1 plus 1 over 8 z minus 2. The usual way of factorization get to numbers, but if you add them, you get this. If you multiply them, you get this one, the product of this. So, because you can see 3 over 4, I can use, well, 3 over 4, I can use 1 over 4 and 1 over 2. I can have this as 1 minus 1 over 4 z minus 1 minus 1 over 2 z minus 1 plus 1 over 8 z minus 2. Because if we perform this, then you actually get minus 3 over 4. If you multiply them, you get 1 over 8, the coefficients. Yeah, we are talking about the coefficients. So that this one I can factorize by having 1 into 1 minus 1 over 4 z minus 1 into um, into okay, minus 1 over 2 z minus 1 into 1 minus 1 over 2 z minus 1. Or basically, I will have 1 minus 1 over 4 z minus 1 into 1 minus 1 over 4 z minus 1. So that's just the factorization of the denominator, and I need to write down my h of z the way it was. So that I have now h of z equal to 1 plus 1 over 3 z minus 1 over 1 minus 1 over 4 z minus 1 into 1 minus 1 over 4 z minus 1. And now this term, we can write it like this, that h of z equal to h1 z multiplied by h2 z, where h1 z equal to 1 plus 1 over 3 z minus 1 over 1 minus 1 over 4 z minus 1, and h2 z equal to 1 over 1 minus 1 over 2 z minus 1. So these are the terms that we need to implement using direct form 2, and then we collect them in cascade. So that we have, if we collect them in cascade, so that we have the block for the h1 z, and then we go to the block for h2 z. So implement each term separately using the direct form realization and combine. So implement each term separately using direct form realization and implement. So the procedure is the same. The procedure is the same. I will have by h1, h of 1 z or z equal to 1 plus 1 over 3 z minus 1 over 1 minus 1 over 4 z plus 1. Then, as usual, I will use the intermediate variable, say y1 of Z over W1 of Z into W1 of Z over X1 of Z equal to 1 plus 1 over 3 Z minus 1 over 1 minus 1 over 4 Z minus 1. Then as usual, we equate one to this term and the other one to this term. So that means I will have y1z over w1z equal to 1 plus 1 over 3z minus 1. That means y1z equal to w1z plus 1 over 3 w1z z minus 1, or simply y1 or n equal to wn plus 1 over 3 wn minus 1. Let me call this one 1. The other one that we have is simply the remaining one, w1 z. I have there w1 z over w1 z over xz over xz equal, actually this does not need to be x1, it is just x. Equal to 1 over 1 minus 1 over 4 z plus 1. Or simply we have w1 we simply have we simply have w1 okay, look at this, there's something here. We simply have w1 z minus w1 z 1 over 4 z minus 1 equal to xz. Or we have here wn minus wn minus wn minus 1. Actually, this should be 1 over 4 equal to xn. Or I simply have here you can say wn actually it doesn't need to be w1 because it's just one. Wn equal to, or if we use 1, we should use 1/3. Yeah, we can use y because we have the second part also. So W1 equal to x1 n plus 1 over 4 Wn minus 1. So that means now we are able to implement the first part of the H1. We are able to implement the H1 part. So we can actually draw the H1 part. If we draw the H1 part, I can start by drawing, actually I will start by drawing this part so that we have the X part first. So we have the Wn as the output, but for you to have the Wn as the output, you need the Wn, then delayed version of Wn by 1 unit, ZZ, C1 by 1 unit, plus the X of n. You can see I will have this. The multiplying factor here is 1 over 4. So here you have the X of n coming in. So X of n, we multiply, we add X of n, is what we have here. Then this other one, we have it here. So we get the W of n. So that is the first part. Then the second part is here. This part where you are going to we are y1 of n, y1 of n, but for you to get the y1 of n, you need delayed version wn and wn minus 1. So we need wn minus 1, z1. Then we need a delayed version of this. See? Actually, we need, just look at this. We need wn minus 1. We already have them. In fact, I don't need the wn minus 1. I don't need this because I have wn minus 1 here. So what we have here is wn. I need wn, a third of wn minus 1. So a third here. Then we add them there. And I have this. So this is my H1Z. Having the input here and the output here. Then now I need to have my, let me call this one X1. Because now I have two systems. In one of them, the input is X1, the output is Y1. Maybe the intermediate variable is Wn1. We can all denote them by 1. So this gives me the implementation of H1Z. Then now let's look at the implementation of H2Z. For H2Z, we have it here. H1Z, here our H2Z, here H2Z. H2Z equal to 1 over 1 minus Z minus 1. So I have I have H2Z equal to 1 over 1 minus a half Z minus 1. So actually here we may not need to use the intermediate variable since it doesn't have a numerator. Okay, so this one, since it does not have a numerator, intermediate variable is not necessary. So we may just go ahead and say H2Z, which is equal to Y2Z over X1Z is equal to 1 over 1 minus 1 over 2 Z minus 1. Or simply Y2 Y2Z minus 1 over 2 Z plus 1 Z, Y2Z equal to XZ. Or in time domain, because you realize when we are doing the diagrams, we go back to the time domain in either direct one or direct two implementations. So we'll have Y2n minus a half Z plus 1 Y2n equal to X of n, X2 of n. Or simply, if we draw this, then you would have X2 of n. You remember the output here is Y2, and so you need a delayed version of Y2 of n, delayed by 1 unit, Z is 1. This will give you this term. In fact, maybe this would be better represented if we write it in this form, that Y2 of n is equal to X2 of n plus 1 over 2 Z plus 1 by 2 of n. Even here we are supposed to have it in form over because we are working in the time domain here. And here I can still, because I'm working in the time domain, Y2 and minus 1. So that I can see I need to delay this. Then after delaying it, I add it to X of n, so that I basically have this value. We need to add it to a delayed version of this to get the Y2 of L. So that here I have a half. So this is what I will have. Then now the two needs to be combined. So we need to combine the two. We need to cascade them so that we have our Y, this one, input X1 giving us the output Y2, and then this output Y2 should be the input X2, or this. So I should be able to draw I should be able to have this circuit which we have here. And then now to get the output y2 here, y2 of n. Just let's have the y2 of n here. So finally, we need to have my y2 of n, the output y2 of n, the output. And then we have the delay, z minus 1. Then we have, let's see what we have here. It goes back to the input. So it goes back there to the input. So instead of having the x2, this would be now the input to the system. So the one that would go there now would be this one. So that now the overall input is x1, the overall output is y2. In which case, here we are saying that y2 of L is equal to x2 of L. The output of this is equal to the input of the second system. Then this one becomes the cascaded implementation of the signal. So I hope this should be clear. Listen to it and then try it on your own and be able to obtain the result. They're different. You can still ask a question and then we look at why there's a difference. You can see that cascade realization is simply need to collect the two signals in cascade. So finally, we need to finalize this lesson by saying something about the parallel form of realization of the filters. So what is it which is in the parallel form of realization? So here, the different systems, so we actually have different IIR systems connected in parallel. So how do we connect them in parallel? If we have a given fraction, then we would obtain the partial fraction implementations to give us the different components that we need to implement. That is, if we, let's just have an example, as, if we can. Because what we are saying here is that we'll have our function h of z. This function, which can be expressed as yz over xz, then we'll be able to express it in terms of partial fractions, bc1 plus c1 over 1 minus p1 z1 negative 1 plus c2 or 1 minus p2 z minus 1 plus up to maybe cn into 1 minus pn z minus 1. Then eventually in implementation, we implement them in such a way that we have h of z equal to y of z, x of z equal to c plus h1 z plus h2 z plus h3 z plus equals. Then each of them we realize using direct form, two realizations, so that eventually we'll have a general circuit given by the input x of z. If we add a constant there, then we'll have a constant c. Then we have we'll have h1 of z, h1z, h2z, we add it to this one comes, we add it here up to hnz, the last one will be hnz. Then we get the output yz. So that all the systems are connected in parallel with each other. So all the systems are connected in parallel with each other. Let's have an example. Let's say we have h of z equal to 3z into 5z minus 2 over z plus 1 over 2 into 3z minus 1. So what we need to do, step 1 is to obtain the partial fraction. Obtain the partial fraction. After you have obtained the partial fraction, which we easily do, and we can just illustrate this, I have hz over z, divided both sides by z, equal to 3 into 5z minus 2 over z plus a half into 3z plus 1. And this one should be equal to two fractions, a over z plus a half plus b over 3z minus 1. Then from here, we have z plus 1 over 2 B plus 3Z minus 1A equal to 3 into 5Z minus 2. So the usual way of obtaining the partial fraction, just reduce this to 0. That is 3Z plus 1 equal to 0. Z equal to a third. If we put Z equal to a third, then what you'll get here, this one reducing to 0, so it will be determine the value of B. So I will have a third plus 1 over 2 B equal to 3 into 5 times a third minus 2. In fact, from here, you'll be able to get B equal to minus 2 over 5. So if you follow the same procedure by reducing this to 0, by setting Z equal to minus 1 over 2, then you would obtain A equal to 27 over 5. So make sure you try and confirm that these are the constants that you will get if you evaluate the same. This means that eventually now, if we substitute them back, then we'll have our h of z over z equal to SL over 5 over z plus I have minus 2 over 5 over z minus 1 over 5. So that we have hz equal to 27 over 5 over 1 plus 1 over 2 z plus 1 minus 2 over 5 into 1 minus 1 over 3 z plus 1. Yeah, this would be a 3 actually. This would be 3. Then now use direct form to implement each term. So use direct form realization to implement each term. So we have now done enough of the direct form to realization. You can go back to the previous videos and see how we are able to implement this. Then now, once you have the different forms, then you only need to implement them. So this left as an exercise for you to obtain the direct form realization of each of the terms and draw them in parallel the way we have discussed, so that you have your input x value n. You have your input. So here we don't have a constant, so we'll just have h1 z, which is this implementation here, and then you have you have the other one, h2 z. Then you add the outputs. You bring the outputs, y1 of z, y2 of z, let them join there. Then you get your combined output, y of z. So that brings us to the close of this discussion on the different structures of implementing the filters. There are others which you already talked about here. Yes, these are the main ones which we are interested in for now. So in our next videos, we'll discuss now how exactly to design a filter. Because for you to implement a filter, you have been assuming you have it. But filters are supposed to implement a given predetermined function. In other words, there has to be a problem to be solved. You design a filter for it. You come up with a filter function, then we can implement it. So we look at the different ways of designing different types of filters before they are implemented. So the dots shall have been collected. By now, discussing how a filter is designed, then now we have known how they are generally realized in analog or digital systems. So that is the end of this discussion on these structures.